Hello everyone, this is Sam Spade and welcome to another Coding Fundamentals and GML tutorial. In this tutorial, we're going to be talking about trees, another type of custom data structure that you can make in GameMaker Studio 2. Data structures, as we've said repeatedly, are a collection of data, the relationships between that data, and how you interact with that data. You can make your own, and in this tutorial, we're going to talk about making your own tree data structure. I do want to stress that this is maybe not a perfect way to make a tree data structure, but it is one way. It works pretty well, and it's really more of an example, a way to think about how you would do it yourself. So in general, a tree is a data structure that has a root value and sort of subtrees of children with a parent node represented as a set of linked nodes. Now we'll see an example of this in a moment because it's a little bit more straightforward than it sounds. But you generally only have one root, only one parent for any of the lower nodes, but each parent can have multiple children. And these data structures can form the basis of a lot of other data structures. In fact, there will be a link to Wikipedia at the end of this. I'd highly recommend going to Wikipedia and looking at all of the different tree data structures that exist. So here is a relatively straightforward example. We have our root, then we have the root's children, and then each of these siblings can themselves be a parent with their own children, have their own siblings. Our tree data structure is going to use strings for the data, but we're not going to enforce it. We're not going to have any checks. We're going to create and add nodes, traverse the tree, and return whether a given node is a child. And that's all the functionality that we're going to build in. We're also going to build it out of arrays, but you could also build it out of maps and lists and probably other things as well. Okay, so here's our code. We have our tree create function, which is going to take an argument. That argument is going to be the root node. Then we're going to have our tree node add function, which is going to take a tree. Then the node we want to add to, so the parent we want to make a child of, and then the new child, or the new node. So we have the world as our root. Then we're going to pass in 3 continents. They're going to be children of the world. Then we're going to add some children to North America, and then some children to Asia. And then we have is child, and so we're going to say is Japan a child of Asia, which it should be, because here we are adding Japan to Asia as a child. Then we have some helper functions as well. So actually, let me just drag this up here. So these are the 3 that we're interacting with, but these 3 functions also have some other functions that they're using. So let's go look at these functions. So tree create, pretty simple. We have our tree, our node. Our tree is an array, so initialize just as an empty array. Then we're going to do tree node create, which will create a node based upon the value that we give it, return a node, and then add that node to the tree. Now you can do this in one line like this. I did it in several lines because it's a little bit easier in the debugger to step through and see how it is working. So let's look at tree node create. So here we simply have our node, which is going to be an array, and the array is going to have the data. So here we can see our representation. We have our node is an array. The array is going to have 2 points. One is data, and one is another array of nodes. I have some enums here for ease of use. So we create our node, which is an array. We add the value as the data, and then we create an empty set of children nodes, and we return that node to tree create, and that's our root. So now let's look at the next function, tree node add. Here, we're going to create a new node with the data that we're passing in, right? So we come over here, we're saying tree node add, say North America to the world. So here's our tree, here's the parent, here's the new child that we're creating. So that's argument 0, 1, 2. So we take data, which again we've set to argument 2. So we take our new data, create a node out of that data. Then we have to get the parent node. So we'll go over tree node get in a moment. And we add our new node to the end of the parent's child node. So again, come over here. This node has an array of children where each of these nodes is a child of this node. So we're just adding that new array to the end. So tree node get, this is one of the more complicated functions. So it takes 2 arguments, which is the tree and the name of the node. The first thing we do is get the first node of the tree. The tree itself is an array with only one node, so we can just do this. We're going to see if that data, so if the data in the node matches the data that we gave it. If so, return the node, it's the root. Otherwise, we're going to see if that node has any children, If it doesn't, then the root has no children and it's not the root, so it's not in the tree. We just return -1. But, and this is the key part, here we get to a function that searches the tree, and we're going to do a depth first search of our tree. So we're going to create a queue. We're going to get the array of the children nodes. We're going to loop through that array and put all of those nodes into the queue, and then we're going to start traversing that queue. This will find the node if that node exists in the tree. We'll then destroy our queue because our queue is a data structure that needs to be destroyed, and we'll return that value, which will be -1 if it isn't found, and if it is found, it will be the actual node. So let's look at tree traverse, the most complicated one. Now this is a recursive function call, and if you are familiar with recursion, then hopefully this won't be that complicated. The first thing we're going to do is see if the queue is empty. If the queue is empty, we're returning -1 because we did not find the node. If the queue is not empty, we're going to get the next node in the queue. Then we're going to see if that node matches the node that we're looking for. If it does, we return the node. We're done. If not, we're going to get that node's children. We're going to add all of their children to the array, and then we're going to recall tree traverse with the queue. And we just keep doing this. So we get a node and we see if that node matches. If it doesn't match, we take all of its children and add it to our queue or our line. Then we look at the next node and see if it matches. If it doesn't match, we get all of its children and add it to the end of the line. Then we look at the next node, see if it matches, and if it doesn't, add all of its children to the end of the line. To look at it visually, what we'd be doing is saying, does this node match? If yes, return the node. If not, get all of its children and add it to the line. Then go to the first node in the line, which in this case would be B. Does this node match? No. Add all of its children to the line. Next node in the line is C. Does this node match? No. Add all of its children. Has no children? D. Does this node match? Add all of its children. G and H. So now this is our line. Do the same thing with E, F, I gets added to the end, G, H, finally I. If we haven't found the value by that point, we return -1. Otherwise, if we found the value at any prior point, we would have stopped and we would have gone up through the function calls and returned it. Finally, for the last function, to check whether or not a given node is the child of another node, and we're doing just direct child here, all we have to do is get the parent node and see if one of its children is the child that we're looking for. If so, return true, otherwise return false. Okay, let's run this. So let's step in, we create our tree. Again, we're going several functions in here. Maybe we'll just go like this. Here we go. So now we have our tree, which is an array, which has a root. That root has the value, the world, and has an array of children, which is currently blank. We return that. Now we have a tree structure up here. Here we go, my tree. The world and its children. So we're actually just going to step over a couple of these for a moment to get some examples. So here we go, we have several children, each of which is a node in and of themselves that follows the same logic. The name of the node, which is its data, and then its list of children. So we have the world, name of the root node, and its children. Now let's actually step into one of these and see how this process works. Tree node add, tree node create, and we're going to save the tree node get for a moment. So we create a new node. Here we go. So we have our new node, which is just Canada and its children. Then we're going to get the node. We're going to step over that for now, and we're going to get we're going to add this node, the new node, to the child array. So our parent node is North America. So let's see. You come over here to North America. North America currently has no children. We're going to add it in. There we go. Now North America has one child node, Canada. We step through this again. You can see that North America has 2 children. Asia now has 2 children as well. So our tree is built. We have our root node, which is the world. Our root node's 3 children, North America, Asia, Antarctica, and then each of those nodes have their own child arrays. North America has Canada and the United States. Asia has Japan and Saudi Arabia. And Antarctica has none. So now we're going to step through the most complicated function, the recursive function call. So come over here. get our tree node get. So here we go. So the first thing we do is get our root node. This is the world node. Here we go. Node. We can see indeed it is the world. You can compare CD84AO, CD84AO. Does tree node data, in other words, the world, match our data that we're looking for, in other words, Asia? The answer is no, so this will skip over. Does our current node have children? So here we can come see that our node, the world, does in fact have 3 children, as we would expect over here. So the answer here is no, so we can go into those children. So now, and this is the complicated part, we create our queue, we take our array of children, then we pass all of those children into the queue. So let's see what this looks like. Tree queue, view as, DSQ. Here we go. We have our 3 children. Again, you can compare these numbers down here. They're the same as these arrays. Now we start a recursive function call. We come in. Is our queue empty? Nope. Get the next node. So we're going to see, here's our queue. View as a DSQ. We know how queues work. Getting the data is going to dequeue it or remove it. So here we go. It's popped off. Queue now is 2. We have our new node. We're going to check this node. If it equals, we return. Otherwise, we're going to add all of this node's children to the queue. So here we can watch this get added to our queue. And now we're going to traverse the tree again. Okay, so we've come into the next function call of tree traverse. As you can see, it's been added to the stack. We go through the same process. Is our queue empty? Well, let's view our queue as a queue. Here we go. No, it's not. It has 4 nodes in it currently. Asia, Antarctica, Canada, and the United States. Because, and this diagram is pretty accurate to what we're doing, except it doesn't have this final node. Let's say we have the world, North America, Antarctica, and Asia. So North America has added 2. So our queue has B, C, D originally. Then we popped B off and added E and F to it. So it has C, D, E, and F. So queue not empty. We continue. Go in. Is there a match? Yes. And so now everything pops off. We have our value. Here we go. We have our value. Asia. That's what we're looking for. Asia. We destroy our tree. We return Asia. And then we look through Asia's children. Just get the array of children. And then we go through that array and we look at each node in that array and we see if that array matches. And indeed, we should find it in our first array. Parents, children, right? Japan. And in our child array, Japan. Return true. And that should say Japan because originally I actually had a tree that looked like this. So I guess this would have been Asia, this would have been North America, this would have been Antarctica, and Tokyo would have been a child of Japan. I just made it a little bit simpler and then I forgot to change it. So it should say Japan is in Asia, and that's it. And so I know this is one of the more complicated tutorials that we've done. And to be honest, when you're dealing with custom data structures, they are generally going to be more complicated because you have to not only understand that data structure, you have to understand all of the things you're building that data structure out of. And depending upon what you want to do with that data structure, as is the case here, you might have to understand other things such as recursive function calls. But the beauty of it is that once you've created this data structure, you can now interact with it like this. 3 simple functions that allow us to create our own trees and then search them. And of course, you could add greater functionality to remove nodes, etc. And you could see how this could be used in a variety of different ways. So our data structure, it's a collection of data, how it's arranged, and the means of interacting with it. We created our own data structure where we define the data and our means of interacting with it. And we built it on top of other data structures. As always, the links in this slide will be below, along with links to the slides themselves and the source code. And that's it. Thanks for watching.